Time began 13.8 billion years ago with the Big Bang. The universe exploded into existence from a singularity. At time equals zero, everything started. Before that, nothing. This is what cosmology tells us. Except it is wrong. The first second of time never existed, not because our measurements are imprecise, not because we need better theories, but because the concept of the first second is fundamentally meaningless. Time itself breaks down at the beginning, and when you understand why, your entire conception of cosmic origins will be permanently destroyed. We measure cosmic history backward from the present. 13.8 billion years ago was the Big Bang. Go back far enough and you reach the beginning of time. Time equals zero, the first instant, the moment when everything started. Before this, there was no time, no space, no matter, no energy, nothing. Then at t equals zero, the universe began. This narrative is everywhere. Popular science, textbooks, documentaries. The Big Bang happened at a specific moment. Time started then. You can point to it on a timeline and say, this is when the universe began. At the first second after the Big Bang, the universe had specific temperature and density. By the first 3 minutes, nuclear reactions were synthesizing helium. The timeline of cosmic history starts at T equals zero and counts forward. But this is wrong, profoundly wrong. There was no first second. There was no t equals zero. The beginning of time is not a moment that existed, and then time flowed forward from there. The very concept of the first second is incoherent when you understand what actually happens at the limits of general relativity and quantum mechanics. Let me explain why the first second never existed and what this means for cosmic origins. First, general relativity predicts a singularity at t equals zero. If you run Einstein's equations backward, tracing the expansion of the universe in reverse, the universe gets smaller, denser, and hotter. Eventually, all the matter and energy that now fills the observable universe was compressed into a smaller and smaller volume. Keep going backward, and you reach a point where density, temperature, and space-time curvature become infinite. This is the initial singularity. At the singularity, the equations break down. Infinite density is unphysical. When your equations give infinity as an answer, it means the theory has reached its limits. General relativity cannot describe what happens at the singularity. The theory is incomplete. Something else, some deeper physics, must take over. But here is the crucial point. The singularity is not a moment in time. It is not t equals zero. It is the boundary of space-time where the concept of time ceases to have meaning. In general relativity, time is part of space-time. Time is a coordinate in the four-dimensional manifold describing the universe. At the singularity, this manifold ends. There is no time coordinate at the singularity. Time does not exist there in any meaningful sense. Asking what happened at t equals zero is like asking what is north of the North Pole. The question assumes a concept north that does not apply at the pole. Similarly, asking about the first second assumes time exists at the singularity, but time is part of what breaks down at the singularity. Stephen Hawking used this analogy explicitly. The Big Bang is not an event at a moment in time. It is the boundary of space-time. Time does not extend to t equals zero because zero is not part of the space-time manifold. The first moment of time, the earliest meaningful time coordinate, is some small but non-zero value. Perhaps t equals 10 to the negative 43 seconds, the Planck time. Before this, the concept of time does not apply. Second, quantum mechanics becomes essential at the Planck scale. The Planck time is about 10 to the negative 43 seconds. The Planck length is about 10 to the negative 35 meters. These are the scales where quantum effects of gravity become dominant. Below the Planck scale, space-time itself fluctuates quantum mechanically. The smooth, continuous space-time of general relativity is an approximation that breaks down. We do not have a complete theory of quantum gravity. String theory and loop quantum gravity are candidates, but neither is confirmed. Without quantum gravity, we cannot describe what happens at the Planck scale. We certainly cannot describe what happens at t equals 0, if such a time even makes sense. But what we do know is that quantum mechanics introduces uncertainty. The Heisenberg uncertainty principle relates uncertainty in energy to uncertainty in time. At the Planck scale, energy fluctuations are enormous. This creates large uncertainty in time. The concept of a definite moment, a specific value of t, becomes ill-defined. In quantum cosmology, the universe is described by a wave function. The Wheeler-DeWitt equation describes this wave function, and it contains no time parameter. The equation is timeless. The wave function assigns probabilities to different three-dimensional geometries, but there is no evolution in time. Time emerges from correlations between parts of the wave function, but at the fundamental level, time does not exist in the Wheeler-DeWitt formulation. This suggests that time is not fundamental near the Big Bang. Time is an emergent concept that arises when the universe is large and classical. At the Planck scale, near the initial singularity, time has not yet emerged. There is no first second because there is no time. Third, the Hartle-Hawking no-boundary proposal offers a specific picture of the beginning. James Hartle and Stephen Hawking proposed that the universe has no boundary in time. If you go back far enough, time smoothly transitions into space. Near the Big Bang, the distinction between time and space disappears. All four dimensions become space-like. Imagine the surface of Earth. You can travel south from the equator toward the South Pole. At the pole, south ceases to be a meaningful direction. There is no edge at the pole, no boundary. The surface is smooth. You cannot go further south because you have reached the place where south loses meaning. Similarly, you can travel backward in time toward the Big Bang, but as you approach the Big Bang, time becomes space-like. At the Big Bang, backward in time ceases to be a meaningful direction. There is no edge, no boundary in time. The universe is finite in time, but unbounded, like the surface of a sphere is finite, but has no edge. In this picture, there is no first moment of time. Time does not start at a specific instant. Time fades into space. The concept of the first second is meaningless, because time at the Big Bang is not time in the usual sense. It is a space-like coordinate. Fourth, inflation provides another perspective. Inflation is a period of exponential expansion driven by a scalar field in the early universe. Inflation began at some time after the Planck Epoch, perhaps 10 to the negative 36 seconds after whatever boundary or transition marks the beginning. Inflation lasted a tiny fraction of a second but expanded space by a factor of at least 10 to the 26. After inflation, the inflaton field decayed, releasing its energy into particles and radiation. This is reheating. The hot, dense state after reheating is what we usually call the Big Bang. The cosmic microwave background, Big Bang nucleosynthesis, the expansion history we observe, all begin after reheating. So the Big Bang in the sense of the hot, dense fireball that produced the matter, and radiation we see is not the beginning. It is what happened after inflation ended. Before inflation, there was something else, perhaps a quantum gravitational state, perhaps a different phase of the inflaton field, perhaps eternal inflation in which our observable universe is one bubble nucleating in an inflating multiverse. The point is that the first second, usually understood as the first second after the Big Bang fireball, is not the first second of existence. There were earlier times, the inflationary epoch. Possibly, earlier epochs we cannot describe without quantum gravity. The beginning is not at t equals 1 second or tu equals 1 microsecond, or even tu equals the Planck time. The beginning might not exist in any conventional sense. Fifth, eternal inflation suggests there might be no beginning at all. In eternal inflation, once inflation starts, it continues in most regions while ending in small pockets. Each pocket becomes a bubble universe. The inflating space between bubbles continues inflating eternally, producing more bubbles. This process has no beginning and no end. It is eternal. Our observable universe is one bubble. The Big Bang for us is when inflation ended in our region and reheating began. But this is a local event. Globally, the multiverse has been inflating eternally. There is no first moment for the multiverse. There is no global time coordinate. Different bubbles have different local times. The multiverse is timeless in a global sense, even though time exists locally within bubbles. This is speculative, but it illustrates that the concept of a first second might not apply even in principle. The universe, or multiverse, might not have a beginning. The question, when did time start, might be meaningless, because time is a local emergent concept, not a global fundamental property. Sixth, loop quantum gravity offers another approach to quantum cosmology. In loop quantum gravity, space-time is discrete at the Planck scale. Space is made of quantum loops, tiny networks of geometry. Time evolution is not continuous but discrete, proceeding in Planck time steps. Some loop quantum gravity models replace the initial singularity with a bounce. The universe was contracting before the Big Bang. It reached a minimum size where quantum effects become important. Quantum geometry prevents collapse to a singularity. The universe bounces, beginning to expand. The Big Bang is not a beginning, but a transition from contraction to expansion. In this picture, there is no first second because there was time before the bounce. The universe might be cyclic, oscillating eternally between expansion and contraction, or there might be a single pre-bounce phase, followed by the current expansion. Either way, the Big Bang is not the beginning of time. It is a phase transition within time. Seventh, the thermodynamic arrow of time and entropy create additional problems for the concept of the first second. The second law of thermodynamics says entropy increases. The arrow of time points from low entropy past to high entropy future. The early universe had extraordinarily low entropy. The cosmic microwave background is extremely uniform, about 1 part in 100,000 variation. This is a low entropy state. As the universe evolved, structure formed, galaxies, stars, planets. Entropy increased enormously. This defines the direction of time. But at the very beginning, near the Planck Epoch, what determines the arrow of time? If the universe was in a maximum entropy state, time would have no direction. If it was in a low entropy state, why? What set up the initial low entropy configuration? The beginning of time requires an explanation for why the universe started in a special low entropy state. Without this explanation, the arrow of time has no foundation. Time as a directional flow only makes sense if there is an entropy gradient. At the absolute beginning, before the entropy gradient existed, the concept of time flowing from past to future is not well defined. This means the first second cannot be understood just as the earliest moment on a timeline. It must be understood in the context of how the arrow of time emerged. And this emergence might not happen instantaneously at t equals 0. It might require a transition period, a quantum gravitational phase where time is not yet flowing in a definite direction. Eighth, cosmological observations cannot probe arbitrarily close to the beginning. The cosmic microwave background is the earliest direct observation. It shows the universe at about 380,000 years after the Big Bang. Before that, the universe was opaque to photons. We cannot see earlier directly. Indirect observations constrain earlier times. Big Bang nucleosynthesis occurred at about 3 minutes. We observe the abundances of light elements and they match predictions. This confirms the hot, dense state at 3 minutes. Inflation predicts density fluctuations that seeded structure. We observe these in the CMB. This confirms something like inflation happened at around 10 to the negative 36 seconds, but we have no direct observational access to the Planck epoch. We cannot observe t equals 10 to the negative 43 seconds. We certainly cannot observe t equals 0. Everything we say about the first second is extrapolation from theory, not observation. The theories, general relativity and quantum mechanics, break down as we approach t equals 0. Our extrapolation is into a regime where we know the theories are wrong. So when cosmologists talk about the first second, they are not describing something observed. They are describing what equations predict, knowing the equations are incomplete. The first second is a theoretical construct, not an observed reality, and the theory tells us the construct breaks down. Ninth, the concept of existence at t equals 0 is philosophically problematic. If time began at t equals 0, then t equals 0 is the first moment that existed. But for a moment to exist requires it to be part of time. If t equals 0 is the beginning of time, is it inside time or outside time? If inside, then it is not the beginning because time extends to include it. If outside, then it does not exist as a moment in time. This is a paradox similar to asking whether the set of all sets contains itself. The beginning of time cannot be a moment in time because it is the boundary where time begins. But if it is not a moment in time, how can we talk about it as the first second? The concept is incoherent. The resolution is that the beginning of time is not a moment. It is a boundary. Boundaries are not part of what they bound. The edge of a disk is not part of the disk. It is the limit of the disk. Similarly, the Big Bang is not a moment in time. It is the limit of time as you go backward. You can get arbitrarily close, but you never actually reach it. There is no first moment. 10th, the measurement of time itself requires physical processes. Clocks measure time by periodic processes. Atomic clocks use electronic transitions. Light clocks use photons bouncing between mirrors. All clocks rely on physical processes unfolding over time. To measure time at the Planck epoch requires a clock that operates at Planck scale. But what physical process could serve as such a clock? At the Planck scale, quantum fluctuations are enormous. Energy and time are uncertain. The very notion of a well-defined time coordinate breaks down. You cannot synchronize clocks. You cannot define simultaneity. Time becomes a fuzzy quantum variable with large uncertainty. The concept of a specific value of t, like t equals 10 to the negative 43 seconds, is not operationally meaningful. Without the ability to measure time at the Planck scale, the concept of the first second is not just theoretically problematic, it is operationally undefined. You cannot point to a physical procedure that would measure the first second. It is not just that we lack the technology. The procedure does not exist even in principle because time measurement requires a physical process, and physical processes are not well defined at the boundary where space-time itself is forming. So the first second never existed, not because something destroyed it, not because our observations are too imprecise, but because the concept itself is incoherent at the limit where space-time emerges from a quantum gravitational state. The popular narrative that time started at t equals 0 and the first second was the beginning is wrong. Time does not work that way at cosmological boundaries. Time is part of space-time. Space-time is described by general relativity classically and by quantum geometry at the Planck scale. Neither description includes a first moment. The Big Bang is not an event that happened at a time. It is the boundary of time. Time does not extend to the Big Bang. Time begins some small but non-zero distance from the Big Bang, perhaps at the Planck time, perhaps later after inflation. Before that, if before even makes sense, time is not a meaningful concept. This changes how we should think about cosmic origins. The question, when did the universe begin, assumes time existed to mark the beginning, but time began with the universe. There is no external time in which the universe could begin. The universe does not start at a moment. The universe is the totality of space-time. It has a boundary in time, but the boundary is not part of time. Does this mean the universe is eternal? Not necessarily. The universe can be finite in time without having a first moment, just like a line segment is finite without having a first point as an interior point. The endpoints are boundaries, not parts of the segment. Similarly, the Big Bang is the boundary of space-time, not a moment within space-time. Does this mean we cannot understand the beginning? Not necessarily. It means we need quantum gravity. We need a theory that describes how space-time emerges from something more fundamental. String theory, loop quantum gravity, or some yet undiscovered theory might provide this. When we have quantum gravity, we will understand the transition from quantum gravitational regime to classical space-time. This transition is the beginning in the sense that is physically meaningful. But even with quantum gravity, there might not be a first second. Time might emerge gradually, or time might be cyclic with no beginning, or time might be an emergent approximate concept with no fundamental reality. The first second is an artifact of thinking about time classically. Quantum cosmology might reveal that time is more subtle than we imagined. The lesson is profound. The most basic questions about cosmic origins, when did time start? What happened in the first second? Assume concepts that break down at the boundary of space-time. We cannot naively extrapolate our intuitions about time to the regime where time itself is forming. The first second never existed. Time began, but not at a first moment. And recognizing this is essential to understanding what physics tells us about the origins of the universe. The beginning is not when you think it is. It might not be a when at all.